first of all, I want to recap again the formulation of the first derivative. What we had yesterday from the Taylor expansion series is we can write that the approximation of the first derivative is really what we expect it to be. Plus, if you take the higher order terms from the Taylor expansion series that did not vanish, then you come up with that. It's 1/2 delta t second derivative with respect to time, plus, if you wish, 1/6 delta t square third derivative of u with respect to time, plus higher order terms. Okay? Does it look okay? Do you remember what we've been doing yesterday? Like we've been approximating. Okay. Then, if we do the same for the or let me rewrite once again the advection diffusion discretization. Sorry, actually, advection upwind discretization. What we had yesterday was that the upwind scheme looks like that. Well, let's maybe take the stable one. Or, okay, anyway. This one will be stable as well. Conditionally, it will be. Okay, so this is the upwind discretization that we finished with yesterday. We remember that that taking the upwind based on the previous time step leads to a scheme that is conditionally stable. And let's see how this what is really represented by this term. And here, following the same procedure as here, we would see that I n minus I minus 1 n divided by delta x equals a times the derivative that we really want to represent. Plus 1/2 delta x second derivative of u with respect to x plus 1/6 delta x squared third derivative of u with respect to x plus.
What about dA in the next?
Sure. Thank you. Okay, so let's ask ourselves the following question. We have got this numerical scheme that we are using to solve the unsteady advection equation. The question is, we came up with this scheme starting with the advection equation, the differential equation that we wanted to discretize. And that's the scheme that we came up with. Right now the question is, okay, if we solve it on the computer, what kind of equation do we really solve? So if we now replace this term by that, this term by that, let's see what kind of equation do we really solve for. And the answer is, we are solving something like that. Third derivative of u plus a du dx plus 1/2 a dx. Second derivative with respect to x is 1/6 delta x, sorry, a delta x squared. Third derivative with respect to x, well, plus higher order terms equals 0. Right now, that's the important part. Let's see. This is something that we do have in the advection equation. So that's something that we really want to have. The next term is something that we also want to have. Right now, see, just by applying the discretization procedure, we came up with additional terms. For example, this one, that one, that we do not want to have at all. The good news is that all the terms vanish if we go down with the time step size down to 0, if we go with the space discretization down to 0. So that's why our scheme is consistent with the equation. So that's the good information. The bad information is that, to be honest, the time step size or the spatial discretization size, they never are 0. So you always introduce some error just based on the discretization. And let's maybe skip that, but I want to very much focus on this term. What is it? What do you associate something that has got the second derivative with respect to space? Diffusion. Exactly. That's diffusion. So you can see that just by applying discretization, and to be honest, more specifically the Upwind discretization in this case, we introduce automatically the artificial diffusion that arises in the numerical solution. What's the coefficient? Something like that. That's the artificial or numerical diffusion that is introduced to the scheme, and that's the real equation that you're solving by applying this scheme. Now the very, very smart way of thinking is, okay, if we know what the artificial diffusion is, okay, the problem right now we've got the pure advection equation. But imagine we have the same problem with advection diffusion equation. And then the argument goes, okay, if we can calculate artificial diffusion, then let's maybe, just if you imagine that we would be solving du dt plus u dx equals some new then the very nice argument goes, okay, if we can calculate the artificial diffusion and we want really to solve such an equation, then maybe simply let's subtract something like that from nu, because then we know that this term that is lowered plus that one that arises due to the application of the discretization would be exactly what we want to have. Smart enough, except for one fact, that in 1D you can really calculate how much it is. If you go to triangular elements, if you go to 2D, if you go to 3D, no. You can't really calculate how much artificial diffusion you're introducing to your scheme. Is this one clear, or do you have any questions?
But isn't the FCD doing such a things in the 2D or 3D? Like, it computes basically the diffusion to make the solution sharper.
Like some flux correction?
Yeah, it's FCD, it's flux corrected transport. Yeah, like it's much more complicated than this formula, but
might be, I don't know. Don't know. But what you have to be aware of is the following. If you take the advection equation, basically it's just a pure transport equation. And question? Okay. And to imagine that you start with such an initial condition for t equals 0, and you've got some advection velocity, then you know that what you would expect after some time is you would expect having such a solution that is simply purely transported. But you won't get something like that in the numerical scheme if you've got your let's say if you've got your space discretization. This one will be really quickly diffused. You will see something like maybe that's something that you would have after just a couple of iterations. And that one is due to diffusion that you have introduced.
I have one comment. Actually, in the formula for the space discretization, there should be minus before the second derivative, and then the minus in the bottom.
Here.
Yeah.
That's true because it's subtraction and should be minus also here.
Minus in the bottom.
That's right. Yeah, and you're right because
that's actually diffusion.
That right now is diffusion. Yeah, yes, you're right. Because diffusion has got the positive sign if it's on the right-hand side of the equation. Yeah, right. Well, so basically, you can observe something like that as the result of the diffusion that you introduce. What's the diffusion? First of all, it's proportional to the advection velocity and the delta x. So you can see how you can reduce that. You can probably reduce this effect by taking smaller space discretization steps. The other effect that you would observe for some of these schemes, well, actually, I think it exists for every scheme, is not the diffusion, but dispersion. Dispersion means that if you want to advect such as an initial condition, then what you can come up with is not that, but maybe this can be something like okay. And if you wait a bit longer, then you can even rise with something like more. Because you will see that you can represent your initial condition by some Fourier series that is composed of modes with different frequencies. And it turns out that most numerical schemes transport different frequencies with different speeds. So after some time, you can see that something like that appears because your initial condition, different frequencies and different modes have been transported with different velocities, and that's the end effect that you would observe. Basically, most of the schemes have got both features, both diffusion and dispersion is introduced by just the sake of introducing the discretization. Questions?
For the term with the time step to the power of 1, just below this here. What did you say about this one?
I didn't say anything.
Okay, because we have diffusion here because of the.
Yeah.
It doesn't disappear, and this one doesn't disappear also.
Well, it doesn't disappear. What is it? Something that is associated with the second derivative is something like the dynamical response. Yeah. If you've got classical mechanics, just the mass on the spring, then you can see, so to say, this is inertia. That's inertia, and that's the second derivative of something.
And actually it contributes to those wiggles at the interface because that contributes, this is the wave equation.
Mm-hmm. Yeah, you can simply remind from mechanics. Yeah, if you've got something like that, or if you've got such an equation, then with no damping, you would simply have oscillations. You can see that probably this term introduces something similar, like a small amount of the possible oscillations that can be introduced to our system. Okay, so right now let's move to something even more important. Right now, let me write the steady state advection diffusion equation. Obviously, this is A du dx equals diffusivity second derivative of u with respect to x. And now the good question is how to discretize it, in a general way, assuming that you want to write a numerical scheme and you don't know whether A is positive or A is negative. How can you write the discretization?
Maybe split these to two terms, one for positive A and one for negative A term, and the positive will be kind of backwards and negative forward, or? Yeah,
exactly. Like the very, very common procedure is probably in the implementation, you can simply use some if statements, but something that is very, very often written in the equations is the following is the following notation. You simply write maximum of A and 0 times ui minus ui minus 1 divided by delta x plus minimum of A 0 times ui minus ui plus 1 divided by delta x minus, and that's a regular second order term that does not have any upwind, it does not depend on the upwind, plus ui plus 1 divided by delta x squared equals 0. Yeah? If you've got positive velocity, then obviously this term is equal to A, and you've got the regular upwind that we had a minute ago. If A is negative, then you need to take the derivative based on needs to be taken the other way. Must be ui plus 1 minus ui, because it's still the same derivative, but needs to be taken upwind, and upwind means then taking I plus first and ith. Yeah. Now, I would strongly recommend you discretizing with find differences the advection diffusion equation in MATLAB, both the steady state and unsteady. Yesterday we had the matrix structure, and I think it's really extremely good from the educational point of view to implement the find differences for advection diffusion equation. I will show you what kind of conclusions you can get to. That's important to see. If we assume for a minute that we've got the Dirichlet boundary conditions, u equals 1 and u equals 0, and let's assume for a minute that we have some viscosity or some diffusivity, but the velocity is equal to 0. What happens in this case? Then obviously is the heat conduction equation, and the solution is, we've got a linear solution. Yeah? Nothing interesting can happen here. If we increase the velocity, then what happens is the solution is more and more advected to the right. If you've got small velocity, you have such a solution. If you increase the velocity, you would end up with something like that. If your velocity is very, very large compared to diffusivity, what you come up with is actually something like that. Maybe not a perfect drawing. What you get here is a very, very steep gradient. And I think it's extremely worth doing because it's the simplest way of seeing what can happen in the numerical procedures if you need to resolve steep gradients for boundary layer, for example. If you've got steep gradients in heat transfer. This means that's really the advection diffusion equation in the steady state is perfect illustration of what can happen. And what you would see is especially playing with delta x diffusivity or velocity is like it's really worth doing, because what you would see is if you've got velocity that is too large for a given discretization, let's assume that you've got just maybe 10 fine differences or so, then you can increase the velocity to a certain value. If you go higher with the velocity, you know that the analytical solution is probably something like that, but your numerical solution will do something different, and you can quickly get something like more or less. Like you get huge oscillation, huge wiggles, that's how people call them. It's a well-known phenomenon in numerical discretization. You can get really huge wiggles if you go with the velocity too high, or if you go with the diffusivity too low. The parameter that describes whether you will get these wiggles or not is called the Peclet number. The Peclet number is A times delta x divided by diffusivity, and if this one is not greater than 2, then everything is fine. And if the Peclet number is below 2, everything will be fine. So you have stable numerical solution. If you go above, then probably small wiggles will start appearing, but if you go even higher, then it's extremely unstable. Now you could ask yourself the question, okay, is it simple to keep the Peclet number below 2? And to be honest, for most physical applications, it's not. Like usually in physics, the diffusivities, whatever phenomenon you've got, like thermal conduction of fluids, viscosity, whatever this should be, mass diffusivity, they are usually like maybe 10 to the power of minus 2, maybe for heat conductivities, probably something like 10 to the power of minus 5 or 10 to the power of minus 6 for kinematic viscosities, velocities that you can have in engineering applications like 10, maybe even 100 meters per second. So, well, how low would you need to have this to keep the whole formula below 2? It like turns out that you probably, for most of the engineering applications, you would need to have, well, maybe 10,000 subdivisions of space in just one direction, and 10,000 in one direction, 10,000 in the other direction. And 3D, it's like good luck with that. There is absolutely no way keeping your mesh, your space discretization and your mesh so fine to satisfy this condition. And that's why upwind schemes are used commonly, because sorry, okay, you would get these wiggles. You would get these wiggles if you apply the central scheme. If you apply upwind, you will not get the wiggles. You will always get stable solution. The problem is that if, let me redraw it once again. The problem with the upwind solution is what? You already know that. Diffusion, exactly. So even if you've got, even if you know that you've got such a analytical solution, but let's assume that your discretization looks like that, your upwind solution will look probably like, even probably not the correct value here, will probably look more or less like that. line, line, line. Now imagine that you want to represent properly the steep gradients, the intensity of the heat flux value, the viscous force, or whatever else. You have no chance of doing that with the Upwind scheme. So once again, you should refine the mesh so that you can represent your gradients on the mesh. And you need to be aware of the fact that, well, the Upwind scheme will give you a stable solution, but in some applications, vastly diffused solution. All right, maybe one last comment to this topic. If we discretize this problem, the advection diffusion problem, let's maybe even do that. What is the matrix structure that you come up with? Let's assume for a minute that we've got positive velocity so that we do not need to put into our matrix these two terms. And let's order it somehow. First of all, we've got ui minus 1, ui plus 1 equals 0, and let's see what kind of coefficients we've got. ui minus 1 is multiplied times minus a divided by delta x. And minus ni divided by delta x squared. Then ui is multiplied by a divided by delta x, and this one does not exist, plus 2 ni divided by delta x squared and here minus ni divided by delta x squared. Well, stupid way of writing that, but right now we've got the coefficients for the matrix. Okay, so again, if we want to discretize the problem along with the boundary conditions, x equals 0, x equals, let's say, 1. Then to implement the boundary condition, and we said that we want to keep u at x equals 0 equal to 1, and u at x equal 1 equal to 0. Then what we want to write here is 1, 0, 0, 0, u1 equals 1. And that's our boundary condition. And right now, this would be minus a divided by delta x, divided by delta x squared. And the second one would be a divided by delta x plus 2 divided by delta x squared minus ni divided by delta x squared. Obviously here 1, many zeros. here 0, zeros everywhere here. That's UN. And there is one more thing that I would like to make evident for you, but I need to think how to make it evident. Okay, now the one thing is, if you have a look at the coefficients that come from the diffusion discretization, so only this, being on the main diagonal, then you should see that if you flip the matrix, then you will come up with the same matrix. So diffusion constitutes always symmetric, always constitutes a symmetric matrix. However, what is introduced by convection always leads to antisymmetric matrices, because you would see that you've got velocity and negative velocity. It's always the case. Whatever discretization you take, whether you take find differences, find volumes, find elements, it's always the case that diffusion will lead to symmetric and positive defined matrices. The convection will always lead to antisymmetric matrices. And now coming to some of the numerical features. If you're solving the diffusion problems, then you come up with SPD matrices, symmetric, positive defined. Positive defined means that, for example, all the eigenvalues are positive. No, actually, symmetric positive defined matrices means that whatever vector P you take times the matrix plus P, then for each P that is not 0, such a scalar product will be greater than 0. But one of the features is that, for example, all the eigenvalues of such a matrix are positive. The good news in the numerics is that you've got a lot of numerical solvers that deal perfectly with such matrices, and it's really easy to solve them. The problem with advection is that you lose this feature. You haven't got adding at least some portion of advection, and antisymmetry to the matrix causes that you haven't got the symmetric positive defined matrices. So, for example, the linear solvers like conjugate gradients will already fail because they are not suited for other matrices than symmetric positive defined matrices. Questions? If you've got time, I strongly recommend you implementing that in MATLAB and playing around with different discretizations, with different diffusivities and different velocities to see that really for Pecklin numbers higher than 2, you end up in a place where you don't want to.
A question about implementing that. What is the most, if we have, I don't know, 1 million rows, what would be the best, the quickest way of implementing that? The quickest way? Quickest way, because one of the courses we had with you and Michał, with several loops, different loops, and which would be the one we
I
should
think
use?
in this case I would take approach that we have a tri-diagonal pattern here, and I will construct basically 3 vectors for each of the diagonal, let's say, and later just kinda concatenate them by diagonal. In this way you don't construct matrix explicit I think. Just creating 3, it's not even 3 rows, it's 3 values basically.
Yeah. But in MATLAB you can also like construct the 3 vectors with the indices, like one with the rows,
Yeah.
the second with columns, and third with a value, and then create a sparse matrix.
Yeah. So probably not iterating by matrix or anything or indices, just creating, abusing like pattern of this matrix.
And then you can go with just one loop.
I don't remember the syntax, but in MATLAB there is, if you use diag at some vector and check it, but I think -1 or something like that, then I think something like that would create matrix that uses your vector v, and I think I might be lying, but something very, very similar would work, that like one place below would be used, these vector values would be used. So then you can add something that is not -1, but is here, and +1 would add something here, and you've got a three diagonal matrix.
And in this case, V is basically one value. It's
Yeah.
A divided by delta x.
And speaking about MATLAB, then V can be created as some, let's say, value times ones of proper size. One of the ways.
In case of diagonal matrix with 3 vectors, you should be able to skip for loops.
Basically, here we are not
Yeah.
using any loops.
Never use loops in MATLAB if they are not necessary.
But in those functions there are no loops.
Here, no loops.
I think internally in MATLAB, no. They explore some vectorization to.
If someone doesn't have the time to implement it on their own, there is actually a tutorial for the CFD toolbox which checks exactly that, like how when you're increasing the velocity in the 1D problem, you will see this this effect with the wiggles.
Right. But I strongly recommend doing that. Like for you, it's probably like 1 hour of implementation, and you learn a lot from that. And you know, it doesn't need to be efficient. When I was writing such codes for the university laboratories to just teach people, and we've been really using for loops. It's one of the slowest way to implement it in MATLAB, but still it lasts 2 seconds. And this one is nice if you want to write efficient code, but I would say using the for loops is nice if you want to keep things evident in the code. And for learning, it's much more important to do it so that you see where you got each coefficient rather than making it efficient. Well, about linear solvers, if you take the backslash operator in MATLAB, so basically ML divide, then that one would solve any matrix that you have. Like, because there is really small, there are many smart algorithms and decision trees that investigate what kind of matrix you got and select, let's say, most appropriate linear solver for that. But if you want to use specific ones, then with with convection, you already run into many, many numerical problems. And I think Konrad can say something about that when you've been implementing the algebraic multigrid with proper preconditioners for the...
Yeah, the preconditioners are best thing in the world, but they not easy to construct always, especially for some flow problems. They are really complicated and often doesn't really work very well. But yeah, without them it's barely converge.